So theme 5 is really about applying our energy balance to PFR and CSTR reactors. And before we can dive into it, there are some basic concepts that you really need to be the boss of, some equations that you are going to use over and over again that you must make sure that you understand before you can proceed. And this is the purpose of this introductory lecture, to do some revision and to make you aware of some of the important equations. So in this course, we are going to apply our attention to steady state flow reactors. So if we have steady state, you will recall, or you may go and revise in your CTD notes or your textbook, that we have no change or accumulation of energy in our system, and that is equal to all the heat flows flowing to or from my system, any shaft work components, and then there is the kinetic energy, potential energy, and enthalpy that comes in with all my flowing streams, and I remove that same energy components with my flowing streams at the outlet of my reactor. We are going to make the following simplifying assumptions. Even for a CSTR reactor where I do have shaft work, I do have a shaft turning that reactor, compared to the other big energy terms in my energy balance, we are going to assume that that energy component is negligible. And we are going to first, of course, also assume that the kinetic energy change of my flowing streams and the potential energy change of my flowing streams is also negligible. And for our first part of this investigation of the energy balance, we are going to focus on adiabatic reactors. So if our reactor is adiabatic, we have no heat flow to or from my reactor. That is why we end up with this shape of my energy balance. The change in enthalpy of my flowing streams must be equal to 0 for adiabatic flow reactors operating under steady state conditions. So of course, in a reactor where there is a chemical reaction taking place, I can have two reasons why there is a change in enthalpy. The first is there is a change in my temperature. And the second is there's a change in the bond energy, so there is a change in enthalpy due to the fact that the reaction takes place in whatever direction is specified. For the change in enthalpy due to the reaction, of course, we are going to use Hess's law, where we use the stoichiometric number of each of my reacting and forming species in the system, multiplied by their standard state heats of formation. So remember the sign over there, so this will be equal to minus 2 times HA formation minus 4 HB plus H of formation of C. The slight glitch here is that we are limited to tabulated values or values available on the web, where we just have certain reference temperatures where we can find these variables. And generally that reference temperature is 298 Kelvin. So in CTD, we realized we could solve that conundrum by realizing that enthalpy is a state variable. And I can design any convenient path to calculate the total change in enthalpy of my flowing streams. So if I have reactants coming in at 500 Kelvin, I would first take it, that's my inlet temperature. We use the subscript naught in CRO and in CKN to denote the inlet. I am first going to cool that down up till the reference temperature where I have information available for my del H of the reaction. So this will probably be 298. Then I'm going to allow the reaction to take place to calculate that portion of the del H. And then finally I'm going to take all my products that have been formed and I'm going to heat them back up to the final temperature. And because my energy balance said that delta H of my flowing streams must be equal to naught, that implies that the starting enthalpy value and the end enthalpy value, the temperature here at the outlet, must be such that the enthalpy of the outlet stream matches the enthalpy of the inlet stream. So what this means is first I'm going to consider the sensible heat of cooling everything that comes in down to that reference temperature. And in our example now, the inlet was at 500. It may imply that you can heat it up, although that will be much less common. In this example, I just use the average CP value. Of course, that can be sum of the integral of everything that was coming in, CPI dt, where you would substitute this A plus BT squared plus C and then just change the temperature from the inlet temperature to your reference temperature where you have your del H available, and that will probably be 298 Kelvin. So for my second step, where I account for the amount of energy change or enthalpy change due to my reaction, I must realize that this then, if I use Hess's law, will have units of joules per mole reaction. So I need to multiply it with something that has got units of mole reaction per second. And that is where you need reminding of our reaction coordinate that we calculated in CTD. So the reaction coordinate is equal to the change in the number of moles of any of the components that participates in this reaction J, divided by the stoichiometric number. And this must now have a sign. So it will be minus 5 for A, it will be minus 2 for B, and it will be plus 1 for C. So for A, for instance, if I want to write the reaction coordinate, it's going to be equal to FA, which is the outlet there, minus whatever was coming in, divided by its stoichiometric number, which will be minus 5. And then if I multiply this epsilon value with my del H reaction, I am just going to end up with joules per second. I can, of course, let's say A is my limiting reactant, and I want to model this by using conversion of A in my reactor. I can, of course, rewrite my epsilon value. This is the delta F of A divided by its stoichiometric number. I can rewrite it in terms of that conversion. So that will show me that it is equal to min FA naught XA divided by min 5, which is then, of course, just equal to FA naught XA divided by 5. So in the example drawing that I've given here, it's important to note that the heat of reaction or the enthalpy change due to the reaction is negative. So this means it must be an exothermic reaction, because I can see del H reaction is smaller than 0. Enthalpy afterwards is less than the enthalpy at the start. If I had an endothermic reaction, of course, the heat del H of reaction would be positive and my figure would look different. I would, of course, have an increase in enthalpy due to the change in enthalpy of the flowing streams with reaction. Nonetheless, now that I have completed step 2 of my imaginary path, I can take whatever is now coming out there and heat it up to my outlet temperature from this reference temperature where I accounted for the heat of my reaction. So it is whatever is coming out, and of course I can write all my outlet streams. I can write in terms of the conversion and using my reaction stoichiometry. So each of the components can be written in terms of just that one dependent variable conversion. For a single reaction, that is often very convenient. So this slide, very important, which I want to show you how to remind you how to get delta H reaction at any T from information that you have at 298 Kelvin. And the equation we are going to use is del H reaction at any T is equal to whatever you have at the reference temperature plus the del Cp of the reaction multiplied by this, whatever the temperature is that you are interested in calculating your del H reaction minus that reference temperature, which in our case will be 298 Kelvin. So this del Cp reaction tells us by how much the heat capacity will change due to the change in bonds in that reaction. And we calculate it just like we would the enthalpy of the reaction using a similar equation like Hess's law. So for our system over here, it will be equal to 1 times the Cp value of component C minus 2 the Cp value of component B minus 5 the Cp value of component A. So this implies that I do not need to first cool my reactants to the appropriate reference temperature, then react and heat up. It just means that I can heat up to that temperature at the outlet and then react at that outlet point. So I have a 2-step energy balance instead of the compared to the 1, 2, 3-step energy balance. So what will remain is first, everything that comes into your reactor must first be heated up to this temperature, which in most cases may be an unknown, this unknown temperature T, and at that T, allow for reaction. So of course, instead of here, you must realize that you've got this equation that now will be substituted in there that will also be a function of that unknown outlet temperature T. So although this equation for calculating del H reaction at any temperature is relatively simple to implement and to calculate in Python as part of any function, whether you are using it in a function that needs to be integrated or one where you are going to apply a solver like fsolve to, this is just an extra algebraic equation in your equation set. Another simplifying assumption that we are going to apply in the first few slides is the fact that for many reactions, this del Cp value, the change in heat capacity due to the reaction is pretty much equal to 0, especially when we compare it to the size of del H reaction. Yes, we might get a value of 20 joules per mole Kelvin or even 50 joules per mole Kelvin. But the del H reaction values, that one that we calculate at 298, is often, it's in the thousands. 8,000, or for an exothermic reaction, joule per mole reaction, is a very mildly exothermic reaction. Minus 50,000, minus 60,000, that becomes significant. So depending on this difference in temperature and the size of this value, it is often quite reasonable to say that this term can be neglected and that therefore my del H of any temperature can just be substituted with the del H that we get when we calculate it at 298. And the reason for that is that although, in this course and in CKN we have A's and B's, and we may lose track of the fact that it's actually not unrelated molecules. It's carbons, hydrogens, double bonds, single bonds, and it forms different molecules, yes, but we still have carbons, hydrogens, so for instance in this oligomerization reaction. So here, the molar mass of B is double the molar mass of A. So we can assume that the energy carrying capacity of B per mole is double that of component A. So what we must just make sure is that we write this as a more or less equal to that. So if I now calculate the mass-based heat capacity of both of them, pause the slide and make sure that you agree with this following statement, is that regardless of a change in the number of moles, that the mass-based heat capacity of my flowing streams, whether I calculate it at the inlet or whether I calculate it at the outlet, where the molar flow rates will be different, and I multiply it with each of the molar heat capacities, that regardless of where I calculate that, it is going to give me the same value because it's the mass-based one multiplied by the mass-based Cp value. Please pause, make sure that you agree with whatever is written there in that text box. Of course, you do not have to guess whether this is true. In all the TATs that I give you, I will give you the Cp values of each of the components so you can test that by calculating the delta Cp reaction. And we are going to give you practice where del Cp reaction is equal to 0 and where it's not equal to 0, and allow you to evaluate what what is the effect? How sensitive is your design or your calculations if I ignore this term, or whether I include it in my analysis? Let's now consider just any arbitrary reaction with stoichiometry as shown to apply this simplifying assumption. So whatever comes into my steady state adiabatic reactor, I heat up from the inlet temperature to that outlet temperature. And then I account for the change in moles at the outlet temperature. Of course, I need the heat of reaction at that outlet temperature, but if my del Cp reaction is very small compared to my del H reaction, I can neglect that term, and therefore I can just use the del H reaction at any temperature where I have available, because I assume that it's relatively independent of changes in temperature. And my epsilon value, my reaction coordinate, please note that I also often describe that using the synonym, the extent of the reaction, can be calculated either based on component A, B or C, just using the correct stoichiometric numbers over there. If component A, for instance, is my limiting reactant and I want to write this del Fa as a function of the conversion of A, this becomes my epsilon value. This is the energy balance I want you to write down before you start. And then think about what is the epsilon value in that reactor that you are busy considering in your analysis. What is important to note here is that for a single reaction, if I make the temperature the subject of my equation, I can get a linear equation that shows how the temperature at the outlet of my reactor will change as a function of the conversion of my limiting reactant. Just remember to apply that correctly. So I can now see that if I have a high heat of reaction, the extent of the change with conversion will be bigger. If I have lots of stuff that must be heated up by that change due to the chemical reaction, if it's exothermic or cool down, it will be buffered by that energy capacity of my flowing streams that must first be heated up or cool down to whatever the temperature is at my exit. So pause on this slide and consider the specific reacting system where I feed pure A at temperature 0 to any steady state adiabatic reactor and calculate what the resultant temperature will be as a function of the conversion of component A by following stepwise the approach that was highlighted in the previous slides. Assumption, del Cp reaction equal to 0 is valid. So once you concluded that you can get to the same linear expression, please apply it to a more, not complicated, but a different reacting system where I not only feed A and B, but I also have an inert that will remain unconverted. So I have A that I feed here, and I've got an inert in my feed. And please see if you can come up with a new linear equation for temperature in the new reacting system as a function of conversion of A and the temperature at the outlet of your reactor. So once again, for my any arbitrary reaction, shown that if del Cp reaction is taken to be equal to 0, get a linear expression of temperature as a function of conversion of my limiting reactant. I can also reshuffle this to make X the subject of that equation and do some algebra. That's not expected of you, but it's very good for illustration purposes to take cognizance of what the slope and the intercept then is in that case. So what I would recommend when you solve these problems is to actually construct figures where X is on your y-axis, so looking like that equation over there, and the temperature is on your x-axis. Even if you use this linear equation and your arrays to get the different values that you are going to plot. What is important to see from the energy balance in this shape, where I might have my X on my Y-axis and my temperature on my X-axis, is if I apply the energy balance, which variables can I change and how will it affect the shape of my energy balance? For instance, if I take an exothermic reaction, let's just reconcile. This has got a positive slope, X versus temperature, positive slope. There's a negative over there. All these terms will give me a positive answer, and of course my del H reaction for an exothermic reaction is negative. So this positive slope makes sense. And if I now have a reaction where the del H compared one reaction to another, if I increase del H, it means that this slope will decrease because I will divide by something that becomes a larger number. So there we go. So what's the implication? For a more exothermic reaction, which is this one over there, the temperature increase is going to be more significant than for that same conversion and a less exothermic reaction. If I inspect equation A over here and I say if I have no conversion, what will the temperature out of my reactor be? This is then simply just equal to T0, your inlet temperature, because there's no heat transfer or reaction that can affect the temperature as it flows through your reactor. So we will have no control over the del H of the reaction. That's governed by the thermodynamics and the nature of the molecules. But we can change the energy carrying capacity of our streams by adding an inert to that mixture. So for the exothermic reaction, for instance, if I increase this, I increase the slope of my energy balance. So I'm going to have an increase in the slope. And if I now look what's the effect going to be for the same X with a higher energy carrying capacity, I will get a lower increase in temperature from my T0 value than when I had my original slope where I did not add an inert into my reacting mixture. What is important to note is that I can apply this to both an adiabatic, must be adiabatic, steady state PFR and a CSTR. So in my CSTR, my inlet will immediately, as it hits that reactor, it will suddenly jump to that outlet temperature. Whereas in my PFR, what I must realize is that there will be a gradual change, if it's now an exothermic reaction, from my T0 value at the inlet to my reactor to that, gradually it will change to that outlet temperature at the outlet. So there's going to be a variation in temperature, and of course that will affect my rate. But overall, over this entire black box system, because it's adiabatic, I can apply that equation. What I can also do is to, for each little v, as I integrate, I can calculate that temperature out by pretending that I'm doing an energy balance from the inlet just to that outlet. Once again, from the inlet, the overall inlet, not of that little slice, from the total inlet of my reactor to wherever I'm busy calculating my rate. From the inlet to there, from the inlet to there, in order to calculate all the temperatures along the length or the volume or the mass of catalyst in my black flow reactor. So why do we care about the energy balance and what the temperature is as a function of the extent or the reaction coordinate? And of course we care because the rate in a chemical reaction is one of the crucial things that will affect our design and will affect the outcome of our reactor. So for instance, let's just take that reaction where I have an elementary reaction in component A. I will have two things that will vary with the extent of the reaction. First, the temperature is going to change according to that energy balance that we have just derived. And second, my concentration is going to change because I can write my concentration as a function of conversion or of the extent of my reaction divided by my volumetric flow rate. So of course we know that our concentration of my reactant will always decrease as a function of conversion or the reaction coordinate or extent of reaction. However, in my energy balance, I can follow two directions with the temperature depending on whether I've got an exo or an endothermic reaction. For an exothermic reaction, it's going to start at T0 and the temperature will increase, and for an endothermic reaction, of course, the temperature is going to decrease. My rate is directly proportional to concentration. So that's a linear dependence. And if the concentration drops, the rate will go down. However, my rate has got an exponential dependence on the temperature. So when the temperature increases linearly, I'm going to see an exponential increase in the rate with temperature. So for an exothermic reaction, I've got these two opposing effects. The pull of the concentration that wants to decrease the rate, and the push of the increase in temperature that wants to increase the rate. And initially, and depending on the size of del H and depending on the size of my activation energy, initially this effect of the increasing temperature exponential effect will always win. So see if you can complete that last slide on this study theme that's not shown here. For an exo, drawing the Levenspiel plot for an exo and an endothermic reaction as a function of conversion of A.